Okay, so it's time to begin. So the Zoom has been acting up, so hopefully it's working right now and hopefully it will stay working throughout the time I'm up here lecturing, but if not, I have an old one that I'll leave posted on Canvas if this one doesn't work out, but hopefully it looks like it's holding now, so keep our fingers crossed. All right, so today's lecture is on a couple of things. First of all, there's two additional gates that you need to know about. So far we talked about the NOT gate, the AND gate, the NAND, the OR, and the NOR, right? We talked about 5 gates. And those 5 gates are sort of considered to be your basic gates. But there's 2 other gates. One's called exclusive OR and one's called exclusive NOR that are also fairly popular. So we'll talk about those. And then we'll do a K-map example that involves exclusive OR and exclusive NOR. And then we're going to go into bit addition and multi-bit addition. And all this has to do with lab 2. Okay, lab 2 is due a week from tomorrow. And lab 1, the locked box lab, that's due tomorrow. Okay, so once we're done with the lecture, and there is an activity, the activity today actually is part of what you have to do for the lab. So the activity kind of ties directly into the lab that has to do came back again. All right, yeah, Zoom's acting up. I have a feeling I'm not going to be able to post this, so I'll just have to go with the old one, unfortunately. I mean, the old one has the same material, it's just from last quarter, so it's the first time Zoom has acted up. I don't know, it's having trouble connecting to the internet for some reason, but. Okay, so anyway, that's the game plan. So, after the activity, if you're not done with the lockbox lab, that's what you should work on since that's due tomorrow. But if you are done with the lockbox, then you can start working on lab 2. But you won't be able to finish lab 2 until I talk about an additional topic, something called structural modeling, Tuesday of next week. Okay, so anyway, that's sort of the game plan. But like I said, we're going to start with these 2 new gates. First, with this gate that's called an exclusive OR. So here's the symbol. You can see it looks just like an OR gate symbol, but it's got an added curve on the input. I call this like the spoiler, kind of like your Lamborghini of gates, if you will. But the exclusive OR, it has a different truth table than any of the other gates. Because an exclusive OR, you only get a 1 out when the inputs are different. When the inputs are the same, you get a 0. Okay, so if you look back at all the other gates we talked about, none of those gates have a truth table like that. So it's unique. That's why it gets its own symbol. And the exclusive, one way that you can write the Boolean expression for exclusive OR is like this, is that we only get a 1 out if you got not a B, or if you have a no, right? Because that's where we're getting the 1s from the truth table. But there's also a shorthand way to write this. So instead of writing what you see here, if you write this, it means the same thing. If you write A and then a plus with a circle around it. Okay, so this means that we would say that F equals A exclusive OR with B. Okay. All right. Now, what was I gonna say next? Oh, the other thing I was going to say is that as far as I'm aware, there isn't a symbol in System Verilog for exclusive OR. So you wouldn't be able to write it in System Verilog like this because there's no, as far as I know anyway, there's no System Verilog symbol that represents an exclusive OR symbol. So you would just have to write it like this in System Verilog, right? Because you know how to write it in SOP, System Verilog. Okay. All right, so that's the exclusive OR. So what do you think is the difference between exclusive NOR and exclusive OR? No, we had an OR gate and OR gate. What was the difference between an OR gate and NOR gate? Truth table wise. What was it? Yeah, it's just opposite, right? Because remember the NOR is equivalent to the OR with an inverter on the output. Well, it's the same sort of thing here, that exclusive NOR is equal to an exclusive OR with an inverter on the output. So with an exclusive NOR, you get the opposite, that the output will be a 1 when the inputs are the same, and the output will be a 0 when the inputs are different. And the way that you would write this as a Boolean SOP is just, it's a 1 for not A, not B, or for A, B. And a shorthand way of writing this, that you could write it like this. Okay, where again, the plus with the circle just means exclusive OR, so it's A, exclusive OR with B, and then the whole thing not, right? Again, that not is just a result of having that inverter on the output of the exclusive OR. Any questions? Explain what? Well, the shorthand, it's just, instead of writing it now, you understand where this comes from? Because this is what we were doing, a few classes ago, right? Like last week or the week before, where we first, from a truth table, we just write that SOP Boolean expression, okay? Well, this symbol, the plus with the circle, it just means what's above. So these are equivalent. It's just, this is a shorter way to write it. But this still represents this truth table, right? It's still that you only get a 1 out when the inputs are different. It's just another way to write it where you're not writing it. Okay. But like I said, in System Verilog, I don't believe there's a symbol for exclusive OR. Like you couldn't write it in System Verilog as A, some symbol B, because there is no symbol for that. So you would actually have to write this out in System Verilog. But when you're doing this manually, like I am with the board, okay? Any other questions before we move on? Okay, well, let's do this K-map example, because this example is going to bring up exclusive OR and exclusive NOR. So if you look at this K-map, you can see that we don't have any groups of 8 or 4 or 2. All these ones are by themselves. Because remember, you can't group in diagonal, right? Remember, the groupings either have to be a square or a rectangle, right? You can't do like the regular groups, and you can't do diagonals. So there's no way to group any of these with other ones. So they're all just single groupings. Okay, so, we would write our SOP equation for F. It would just be not A, not B, not C, right? That's what I get. 1 that's in the 0 cell. And then I would have not A, B, C. Right, that's what I would get, right? And then for the number 5 cell, I have A, not B, C. Right, and then for 6, I would have A, B, not. Right, so everybody say I'm just writing basically the index in. Just double check, make sure I didn't make a mistake. That's all right. Again, you see I make a mistake, let me know. Okay, well, when you have a case like this where you have single groupings that are diagonal from each other, there's a good chance that you can actually do some manual reduction where you can simplify this with exclusive OR and exclusive NOR. So what I mean by that is, in a base 2 equation, a Boolean equation like this, just like in a base 10 equation, you can factor out a common variable. So here, for these 2 terms here, I'll factor out a not A, right? You see, I can write it like this. These 2 terms here, I can factor out an A, right? I'll factor out an A. Now, there's more than one solution to this, by the way. I mean, you could, do different factoring, but I'm just showing you this one here. You see, I just factor out the not A here, A there, and now, once I factor out the A, now if I put the parentheses. What do I have here? What's this not B, not C, or with BC? What's that equal to? Yeah, that's this right here, right? It's an exclusive norm. And then how about right here? What's this? Exclusive OR. So I can write this as this would be B exclusive OR with C, the whole thing knotted. Nice, so that's this down here. And then here I could write this as B exclusive OR with C. Right? That is right up here. Can I go further? Can I reduce further? What if I did this? What if I used the dummy variable? You use the dummy variables, right? Like in calculus, where you just assign like a variable just as kind of like a placeholder thing. What if I did this? What if I set X to B exclusive OR with C? So then I could write this as not A, and then this would be not X, right? OR with A, and then X. Right, because I'm just substituting in a dummy variable for this B exclusive OR with C. But now, can we go further? So it's this. Exclusive NOR. Yeah, it's exclusive NOR with A and X, right? So just equal A exclusive OR with X, right? All knotted, and then just put in X. And when you're exclusive ORing terms, it doesn't matter the order of the terms. Just like when you're ORing things together, or ANDing things together, the order doesn't matter. Same thing here. So I could write this in any order. Okay? But you see, that would be the most reduced expression. It's right here. Okay. So one of the reasons why I talk about these gates and I give you this example today is because for the activity, which is prep work for lab 2, you are going to run into this. Okay, you'll see that for the activity for lab 2, there's a K-map that looks similar to this. Okay, it's not exactly this one, but it's similar. And you can do the same thing. Same approach as what I did here. Okay. All right, so any questions up to this point? Because this is all I needed or wanted to say about exclusive OR and exclusive NOR. The rest of the class is going to be about bit addition, both singular bit addition and multi-bit addition. And then that's going to lead into the activity, which is part of the lab 2 prep. And then I want to talk about lab 2, the first part of it. Again, you're not going to be able to do all of lab 2 after today because you need more information that I'll talk about on Tuesday. But then I also want to talk about some general troubleshooting because, you know, now that you're starting to get into the labs and, you know, lab 1's a little bit more complicated than lab 0 was, you know, people are starting to run into problems. So I want to start talking about, you know, what approach to take when, you know, your Verilog, your system Verilog program is not working. Okay, there's like a systematic approach that you can take. Okay, so we'll talk about that. But any questions before I continue? Oh, everyone's okay? All right. All right, well. The next thing we're going to talk about are the single bit addition rules. And here they are up here, at least most of them. So if you're adding 2 bits, then there's 0. The result is 0. If you're adding a bit that's 0 and another bit that's 1, result is 1. If you're adding 1 and 0, just a different order, doesn't matter the order, it's still 1. And then if you're adding 2 bits and they're both equal to 1, well, that obviously is 2. And then how do we write 2 in binary? 1, 0. Okay, so next time you talk to your parents, tell them that in your freshman level, Cal Poly, college level class, you learned what 0 plus 0, 0 plus 1, 1 plus 0, 1 plus 1 was equal to. They'll be so proud. All right, but what we're gonna do next is we're gonna put these rules into a truth table. Okay, because one thing that should be becoming apparent at this point, Zoom is back, so like there's a poltergeist or something with Zoom today. It comes on and off when it wants. One thing that should be apparent from what we've talked about thus far this quarter is that if you can put something into a truth table, well, you can get a logic circuit from it, right? Because we've shown that. We've shown how you can write either an SOP or a POS equation from a truth table. And then once you have that equation, you can represent it with logic gates, okay? So that's the reason why we're going to put these rules into a truth table, because then we can actually see the logic circuit that performs these rules, right? And that logic circuit would be a bit adder, if you will, right? Okay, so in order to put this into a truth table, I'm gonna label the top row bit A and this row bit B. And then in the result, I'm gonna label this bit F. Okay, and I'm gonna label in the result this bit to the left of the F bit, I'm gonna label that C. And I know I don't have to put the zeros here, but I'm gonna do it anyway, just to make it clear. Okay, so I'm just assigning variables to the bits, so I can put it into a truth table. So now the truth table, and remember, by convention, truth tables, the inputs go on the left side and the outputs go on the right side. I think this is the first time we've seen a truth table with 2 outputs, right? All the other truth tables just had a single output, but you can have as many outputs as you need, okay? There's many, and in fact, we're gonna see a truth table, I don't know, in a few classes that's got like 7 outputs. Okay, this one's got 2, C and S. Okay, so now we fill in for this rule here, when A and B are both 0, well, C and S are both 0. Okay, this rule here, when A is 0 and B is 1, C is 0 and S is 1. Here, when we have 1, 0 at the input, the output's going to be 0, 1. And then when both bits are 1, the output's going to be 1, 0. Okay? Now, we could take this 4-row truth table and put it into a 4-cell K-map. I mean, there is such a thing as a 4-cell K-map, just like you have an 8-cell from an 8-row truth table and a 16-cell from a 16-row truth table. But the thing is, really 4-cell K-maps are kind of useless, really, because when you only have 4 rows in your truth table, you can get what logic gate you need for an output by just looking at how the output relates to the inputs. So for example, if you just look at output C, just ignore output S, just look at output C. Output C is a 1 only when both inputs A and B are 1, right? Otherwise it's a 0. Well, you should know what gate that is. We talked about that gate, right? What gate gives you a 1 out if only all the inputs are 1? And exactly. So if I take an AND gate and I put A and B into it, I'm going to get output C out. Okay. All right. Now just look at output S. Output S is only a 1 when the inputs are different, right? Output S is a 0 when the inputs are the same. Well, we just talked about that gate earlier today for the first time, right? What gate is that? Yeah, that's the exclusive OR. So if I take an exclusive OR, and also put A and B into it, I get S out. So you see this circuit of 2 logic gates, an AND gate and exclusive OR gate, it gives you this truth table. This truth table came from these rules of single bit addition. So that's what this circuit can do. It can do single bit addition, and it's called a half adder. Okay, so it's a logic circuit that can do binary addition, right? Single bit addition. So any question on how I got this half adder? Now, half adders, all fine and good. However, most of the time, when you're doing like meaningful addition in binary, you have more than one bit, you have multiple bits. So for example, adding multiple bits like these two is more practical than just, single bits. In fact, what are we adding here? What are these two numbers in base 10? What is 0, 1, 1, 0 binary in base 10? 6? I've heard someone say 6. That's 6 in base 10. How about 0, 1, 1, 1? So you see this example is adding 6 plus 7 in binary. Well, when you add multi-bit binary numbers, you add them in the same fashion as when you add multi-digit base 10 numbers, right? You start with the least significant and you work your way to the left. So when we add these two together, we start with the least significant bit, right, which is always furthest to the right. And then we're just using those rules. So 0 plus 1 is 1 and there's no carry. But here we have 1 plus 1, which is 2, so 0 with a carry of 1. And you see now we get to this column here where we're adding 3 bits that are equal to 1. 1 plus 1 plus 1. Well, adding 3 bits, a half adder cannot do that, right? Because a half adder only has 2 inputs. Okay, so a half adder cannot handle the addition of 3 bits like 3 ones. See, that's a drawback of a half adder. Okay, when you get into a situation like this, when you're doing multi-bit addition, half adder isn't going to help you. Well, fortunately, there's another logic circuit that's called a full adder. Okay, and a full adder has 3 inputs. Okay, usually those inputs are labeled A, B, and then the third one is labeled CI, usually. And the full adder also has 2 outputs, just like the half adder does. One of them is S, and the other one is usually labeled C0. Can you guess what the CI and the C0 stand for? Carry in and carry out. Yeah, CI is carry in, C0 is carry out. And this is the truth table for the full adder. Okay, so since the full adder has 3 inputs, how many rows are going to be in its truth table? 3 inputs where each input can either be a 0 or 1 is going to give us how many unique combinations? 8. How do you figure it out? What's the formula? I gave you the formula, didn't I? I gave you this formula, didn't I? Where, let's see, you can write it right here. The number of values or bits, yeah. Yeah, input through bits. But yeah, number of values that you can get from a certain number of bits where here, each bit is an input, is just 2 to the end where this is number of bits. Right, so if you have 3 inputs, 3 bits, that's 8 unique combinations of zeros and ones. If you have 4 bits, 16, 5 bits, 32, right? Every time you add a bit, you double the number of values you can represent with those bits. Okay, so we're going to have 8 unique combinations. So I'm going to put them in binary order. 0, 1, 2. I think I mentioned that in an earlier class, right? When you're doing a truth table, by convention, we always put the binary inputs in binary order, though they're binary numbers. Okay, so 0, 1, 2, 3, 4, 5, 6, 7. I always double check because it's easy to make a mistake. All right, so now to get what the output of the full adder is, we just add these individual bits here. So if all the bits are 0, your result's going to be 0. If you have one bit that's equal to a 1, well, then the result is going to be a 1, right? So we'll have a 1 here as a result, a 1 here, 1 here, right? Because those are all the inputs that just have one of the 3 inputs equal to a 1. And then any row that has 2 bits equal to a 1 on the input side is going to give us a 2 output. 1, 0, right? So we have 1, 0 there, 1, 0 here, and 1, 0 here. And then when we're adding 3 1s, the result's going to be 3. So what do I put here? 1, 1. Okay. Now, to get the expressions, the Boolean expressions reduced for this full adder, that's when you're going to use a K-map. And because you have 2 outputs, you're going to need 2 K-maps, right? The K-map for each output that you have. So this is part of the prep work that you're going to do in the activity for lab 2. Is you're going to find the reduced expression for S and the reduced expression for C0 using an 8-cell K-map. Right? I'll let you fill in the rest of that. Okay? Question?
So it's like future cases of there being like 6 plus outputs, are there like more efficient ways of going about it, or do you literally have to do like 7 different game maps?
Yeah, it's K-map per output, because remember, that's what goes in the squares, right? In the squares goes the value, the 0s and 1s for that particular output. So yeah, in fact, like I said, in about a week or so, there's something that we talk about where there's 7 outputs. Now, we don't use K-maps in that particular case, because you're gonna learn a technique in Vivado, which does a lot of the work for you. But if you did do that manually, right, 7 outputs, you'd have to have 7 K-maps. Yeah, it's a K-map per output. So you see, with the full adder, you can now complete this, right? Because if I have a full adder, I can add 1 plus 1 plus 1. It's going to be 1 with a carry of 1. And I would just end up with a result of 1, 1, 0, 1. And what's this in base 10? What should it be? Because we're adding 6 and 7, so it should be 12, 6 and 7, 13. Yeah, 13. See, got an 8, we got a 4, and we got a 1. Now, when you fill in these K-maps for the full adder to get the reduced SOP equations for those outputs, you're going to find that one of these K-maps, I'm not going to tell you which one, because you'll discover it on your own. But one of those K-maps is going to look similar to this example. So you see, one of these outputs is going to have a Boolean expression that has exclusive OR, exclusive NOR in it. Okay, the other one won't, but one of them will. Okay. Okay, so the next thing is the activity, like I mentioned earlier, is a portion of the lab 2 prep. So let me show you on Canvas what part of the lab 2 prep I want you to do for the activity. This is the warm up. Okay, so for lab 2, and for the activity today, the portion of the lab 2 prep that I want you to do is this part 1, part 1, number 1. Okay, so just this here, where draw a black box diagram And I want you to draw a black box diagram for both the half adder and the full adder. Right, so you'll have a black box diagram. Half adder and full adder. Right, so you have two black box diagrams. And again, what's the purpose of the black box diagram? Like, what does it show you? Yeah, just your main inputs and outputs, right? Okay, so that should take you all of 5 seconds, right? Okay, truth table for both. Well, I gave you those, right? They're up there, so you just gotta copy down what I gave you. Okay, so truth tables. Okay, also, I want you to do the K-maps. Show the K-maps. For both. And then determine the reduced SOP form. So that's the big thing. Determine. Reduced SOP for, well, I essentially gave you the half adder ones, but still write them down. So, you know, you want for the half adder, you want CNS, and then the full adder, you want CONs. Okay, so you'll have 4 equations. Okay, now the rest of this is part of the lab work. Okay, once you are done with the activity, and again, if you haven't finished the lockbox lab 1, you should do that. But if you're done with the lockbox and you want to start into lab 2 today, after the activity, you can then design the half adder and the full adder in Vivado. So you see lab 2 is now getting a little bit more complicated than the first 2 labs, because in the first 2 labs, you only had 1 design source and you only had 1 sim file. Here, you're going to have 2 design sources, and each design source needs its own sim file. So, you know, like I mentioned in an earlier class, for all the labs, have a separate project. So, you know, right now, you should have 2 projects, right? You have a project for lab 0, a project for lab 1. Create another project now for lab 2. And within that project for lab 2, you're going to have a half adder design source, and you're going to have a full adder design source, and you're also going to have a half adder test bench, and you're also going to have a full adder test bench. Okay, so your half adder is going to have its 2 equations, right? So you'll have 2 assigned statements, for, you know, 1 for S and 1 for C. And then your full adder design source is going to have 2 more assigned statements, right? 1 for S and 1 for C0. And then how many test cases are you going to have for your half adder? You're going to have 8 for the half adder? 4. Yeah, remember the way that you get your test cases, it's just look at the truth table of what you're trying to test. Okay, the half adder, you only have 2 inputs, so it's only going to require 4 test cases. How about for the full adder, how many test cases? 8. That's the one that's going to need 8. Okay. Now, a couple of suggestions I have, and this kind of ties into troubleshooting. You know, when I have a student that meets with me and like their simulation's not working for some reason, right? They're not getting the correct timing diagram. Like sometimes they'll have red or blue signals, other times it's all green, but the data doesn't make sense. Okay. Well, if there's a problem with simulation, like you're not getting the correct timing diagram, the problem can either be in the design source or it can be in the sim file. Okay, it could be either of those 2. Okay. You know, some of the common things that cause like blue or red, if you see a blue or red signal in your timing diagram, that means either an input or output is not declared correctly or something's not connected right. Okay. Like a common thing is in your sim file, after the UUT, where you put the dot, some name, like the name of an input or output from your design source, and then in parentheses, you put the name of a input or output of your sim file. Well, sometimes people forget a dot, or they don't put the same name, like they make an error and they don't put the TB, or something like that, something syntax wise. Okay. So anyway, those are the types of things to look for. And also, as you're doing a design source or a sim file, if you ever get a red line under your text, that red line means there's a syntax error. Now, sometimes it's not right on that line where the red line is. Sometimes it's the line above or the line below. But you should never run a simulation if you're getting red lines, because if you have red lines, the simulation's not going to work. Okay. Okay, another thing with troubleshooting is that, if your simulation's not running, or sometimes, like, say your simulation is good, but the bit stream doesn't generate, you'll get errors or warning. And, students get frustrated, and I get frustrated too, because if you look at the actual text of the error or the warning, it usually is gibberish. You look at it and, it's a lot of times it's not coherent, and, it doesn't make any sense. Okay. But what can be useful is two things from the messages. A lot of times within the message, okay, like if you look past all the text, and a lot of times there's a lot there, but you'll see, if you look, a lot of the times there's a link. It'll be in blue. And that link is where the problem is, or at least where the problem is near. Okay. So like when I get an error message or a warning message, I never really read the text because I know it's not going to help most of the time. I just click on that blue link, because that takes me to either the design source or the sim file or the constraints file in some cases that it doesn't like. And again, sometimes the link won't take you to the exact line where the error is, but it'll take you close. Okay, and you just got to kind of focus and see if you see anything wrong at that point. Okay. So that's sometimes it doesn't give you a link. Sometimes instead of a link, it will give you a long path name, a file path name. It'll tell you like C drive, this folder, this folder within this folder, this file. And if you follow it down, usually it ends with a log file, like a .log file. Okay. Well, if you ever get that, find that log file and open it up, because a lot of times the log file has useful information. Like it will have some text, but it's usually more useful than the text in the message. Okay. So those are some of the things that, when things aren't working, you can, first look at it. So, if you don't get a good simulation, like I said, the problem is usually within the sim file or the design source, or both. It could be both. Now, if your simulation is good and it fails during implementation or generating the bit stream, chances are the problem's in the constraints file. Okay. The constraints file has nothing to do with the simulation. Okay. Only the design source and the sim file matter when it comes to a simulation. The constraints file, what that file is doing is it's taking your names of your inputs and outputs and associating it with hardware that's on your board, right? So like when you put a name for a switch, the software is taking that name and associating it with a physical switch that's on the board. And same thing for LEDs for like an output. Okay. So, during implementation, that's when that association is happening, and it needs it for the bit stream. So if it fails anytime during that, there's usually something with the constraints file that's not right. And a common thing, in fact, this has already come up a couple of times this quarter, a common mistake when people edit the constraints file is they delete a parentheses, or there's like square parentheses and there's braces, the curly brackets, and they'll like interchange them, or they'll accidentally delete one, or they'll have an extra one. Parentheses cause all kinds of problems with the constraints file. Okay, so you just got to be really careful when you're editing the constraints file not to mess up the parentheses or the braces or the brackets. Okay. All right, so those are some of the things. Now, Vivado sometimes is just quirky, and there have been cases where, somebody runs a sim file and a simulation, it runs great. And they say, oh, they're all happy because they're done. Then they go home and they run it at home and it doesn't run. And they can't get it to run, no matter how they try. Sometimes that can be a computer issue, and sometimes it can just be like a quirk with Vivado. Like, there's been cases where students have run into that problem and they just close Vivado, reopen it, and it works again. Or in some cases, they have to close Vivado, restart their computer, and it works again. Okay? So yeah, there's stuff like that happens. The key thing is just to be persistent. Eventually, you'll fix it if you just don't give up. And I'll talk more about troubleshooting in a couple of classes when we start to know more about what's called structural design, because there's another technique that we'll use when we get to bigger designs that are structural that, again, is another technique of troubleshooting. But for right now, those tips that I gave you should take you quite a ways. Now, if you do all that and you're still having a problem, that's why I'm here, and Ratchet comes in here the last hour also to help with the troubleshooting. Okay. Oh, but one thing I want to mention, getting back to this here, is that when you have multiple design files and multiple sim files, when you go to simulate, you have to tell Vivado what the top module is. Okay, so let's say you've got these 4 files and you want to simulate the half adder. Well, there's this icon. It's a little pyramid symbol. I don't know if you've noticed it at this point. But you have to make sure that pyramid symbol is in front of both the design source for the half adder and the sim file for the half adder. Okay, that identifies it as a top module. So if you have this, you can go ahead and simulate the half adder. When you go to simulate the full adder, you're going to have to assign the full adder design source and the full adder sim file as top module. And the way you do that is you just click on the file, you right click on the file, and there'll be a pull down window, and you'll see there's something that says set as top. Okay. If you have the half adder as the top module and you get the full adder sim file as the top module, the sim's not going to run correctly. It either will not run at all, or it may run but give you the wrong data because it's using the wrong test cases. Okay. Let's see. Was that all that I wanted to talk about? Let's see. So yeah, because you know what to do for the lab. So like I said, for lab 2, you can't do it all, but you could do part 1. You could do a design source and a sim file for the half adder and also the full adder and test them out, make sure they sim correctly, but you wouldn't download anything yet. Okay, you won't be ready to download anything for lab 2 until you know part 2, which I'm going to talk about on Tuesday of next week. Okay, that's when you're going to learn about structural modeling. Okay. All right. So do you have any questions about anything we've gone over today? Okay, if not, the next thing to do is the activity. Now, I don't have a handout for the activity this time because, like I said, I just want you to do part 1, number 1 of part 1, just this. Okay, and my answers are up here. And then once you're done with the activity, like I said, if you haven't finished the lockbox lab 1, I would work on that because that's due tomorrow. If you're done with lab 1, then you can start to work on lab 2. But again, that's lab 2 is not going to be due until a week from tomorrow, so you got time for that. All right. So any questions before you get started? All right. If questions come up, they'll be up here. I'm gonna post this video. I think there might be like a gap in it, but I'll post it. Actually, I think I'll leave my old one up too. So in case there's a gap, if somebody wanted to watch it, they could just, where there's the gap, they could watch the old one.